4.6 billion years ago, a dense pocket of a massive molecular cloud collapsed inward under its own gravity. It was a violent, chaotic storm of swirling gas and dust. The center of that collapse grew incredibly hot and dense until it ignited into a star, pulling in nearly all the surrounding material. Today, the Sun holds an overwhelming 99.86% of the entire system's mass. Every planet, moon, asteroid, and comet in existence was built from the scraps. Combined, they amount to barely over 0.1% of the remaining material. Yet this scattered, chaotic debris didn't stay chaotic. It eventually organized into highly segregated, perfectly ordered planetary zones. How did a single star physically sort a massive debris field into distinct planetary neighborhoods? We usually picture the planets as isolated, independent worlds. They aren't. This entire structure operates as a massive 4.6 billion-year-old sorting machine, where an object's physical reality is strictly governed by its distance from the central star. In the orbits closest to the newly ignited Sun, the environment was incredibly hostile. Intense thermal radiation and a powerful solar wind blasted lighter, volatile gases, like hydrogen and helium, far out into space. With the lighter gases stripped away, only heavy, dense, refractory materials, metals like iron and nickel, along with silicates, could withstand the heat without vaporizing. Because these heavy elements made up a tiny fraction of the cloud, the worlds that coalesced here couldn't gather enough material to grow very large. This extreme material scarcity is why Mercury, Venus, Earth, and Mars are small, dense, and rocky. Looking at this map of the system, we draw a sharp boundary at roughly 5 astronomical units, 5 times the Earth-Sun distance. Here, solar radiation drastically dissipates. Past this threshold, the frost line, temperatures drop so volatile, compounds like water and methane remain permanently frozen. A planet's foundational building blocks, whether it forms as a sphere of bare rock or a massive globe of ice and gas, depend entirely on which side of this invisible thermal line it happened to coalesce. Because frozen volatiles were vastly more abundant than rocks and metals, planetary cores forming past the frost line accessed significantly more building material. These outer cores grew to be exceptionally large. This chart compares planetary mass across the system. Notice how Jupiter and Saturn completely dwarf the inner rocky worlds. Once massive enough, their gravity captured the abundant hydrogen and helium gas pushed from the inner system, birthing the giant planets. Together, Jupiter, Saturn, Uranus, and Neptune possess roughly 99% of the system's non-solar mass. They act as secondary gravitational tyrants, dominating the outer orbits. Moving past Neptune, we enter a third distinct zone. The Kuiper belt is a chaotic, wide ring of frozen planetary leftovers that never accumulated into a full-sized world. Early in the system's history, the giant planets migrated outward. Their immense gravitational pull perturbed these icy remnants, scattering dwarf planets like Pluto into highly eccentric, tilted trajectories. The architecture of the outer system is defined by these few massive gravitational bullies, sitting isolated within a wide field of the frozen, shattered debris of their own formation. We often assume the orbit of the furthest dwarf planet marks the end of the solar system, but the Sun's physical reach extends much further. At roughly 120 astronomical units, the Sun's charged plasma crashes into galactic dust, creating a turbulent boundary called the heliopause. Past this bubble, gravity holds on. The Oort cloud, a shell of trillions of icy objects, stretches to the absolute limit of the Sun's Hill sphere. This distant edge represents the exact mathematical limit where the Sun's gravitational potential finally surrenders to the gravitational pull of the Milky Way galaxy itself. The Sun's empire is vastly larger than the planetary orbits, carving out an immense, protective bubble stretching light-years deep into hostile interstellar space. Zooming out into the Orion Cygnus arm of the Milky Way, our local neighborhood is filled with a vast array of other stellar systems. But observations from the Kepler Space Telescope reveal a surprising fact. Our neatly ordered, perfectly segregated arrangement of planets is actually a severe statistical anomaly. The average planetary system contains super-Earths, rocky planets between 1 and 10 times our mass, and features planets with highly elliptical paths. Our system completely lacks these intermediate worlds, and our orbits are unusually circular. Evidence suggests our early system likely started with many close-in planets. However, violent gravitational interactions and massive collisions pulverized these intermediate worlds, ejecting the debris and leaving behind only the distinct extremes we see today. Earth enjoys a stable, nearly circular orbit within a calm inner zone, shielded by outer gas giants that cleared out dangerous debris billions of years ago. Our planetary sanctuary is the direct product of an incredibly rare, perfectly balanced architectural sorting machine.